Well, thanks so much for inviting me to speak today. And I thought it would be fun if I had to give Melanie's presentation and she gave mine. I'll talk about robotics at Disney Research. I first talk briefly about Disney Research and then about robotics. So we have two labs. One of the labs is here in Zurich at Stampfenbachplatz, so very close to here. And that lab actually focuses on studios technology, so filmmaking, technology for filmmaking. There's a second lab based in Glendale in California, and that focuses more on what Imagineering does. Imagineering is the branch of our business that focuses on theme parks, and especially also robots. So I lead a team that is based in Zurich. Most of the team members are based in Zurich, but I'm actually part of Imagineering, so I'm a bit of an outlier. So the mission of our team is to create the science behind the magic, basically drive the value by injecting scientific and technological innovation. So we are a relatively small team between academia and basically what the company needs. All right, so let's talk about the team that I lead and the research that we do, robotics. So our use case is different to many use cases here. We actually want to create robots that become physical representations of characters that we know or you know from our movies in the end. And that's actually very challenging as a task because we want to build robots that are perceived not as robots, but as believable characters. So they should pass the Turing test, but not when it comes to natural language processing, but when it comes to the design and control. So we want to build robots that you can't tell apart any longer from the characters that you know from our movies. So software will play a key role. I think we saw that earlier also in other presentations. We believe software is the key to unlock the potential of building ever more believable robotic characters. So we have model-based tools that I'm going to briefly talk about, and they're well suited for building robots or controlling robots that act on stage. So this Iron Man figure you can actually see at Disneyland Paris, and it does a predefined animation in the end. So if you don't have uncertainty, model-based are actually really good tools to control these robots. Learning-based tools are the tools of choice if you basically have an uncertainty in your environment, especially here if you want to walk over uneven terrain. So we'll talk about these tools or these two sets of tools in the context of these three robotic characters. And let's start with the Iron Man figure here. So this is how the Iron Man looks like, and what's actually driving that is our A1000 platform. That's not something that we create here in Zurich. That's important to mention, but we build tools that scale to that complexity level. So you see that this system is quite complex. It has over 100 moving parts. It's made with over 1,000 components for sure. It has kinematic loops, so the two legs are connected to a base in the ground, and we use linkages to place actuators where there is actually space. So highly complex general mechanism in the end. So we want to build tools that can scale to this complexity level, and only if they're generic enough, they can actually be useful. So we'll build here in Zurich a tool that can solve an inverse kinematics problem at that scale. So we can transfer motion capture data onto this figure and abstracting away the complexity of that robot completely to our artists. But we also look into the future more and do research here. For example, we looked into building very light and soft systems. So this is a child-sized robotic character here. That's the animation input. It only weighs 1.8 kilograms without the base. And we wanted to see if we can control very soft systems like that. So here's a simulation. That's usually the first step that we do, is to build a simulation representation that can actually predict the behavior. Here, if you send the unfiltered animation to the robot. So you see the vibrations, we can predict these vibrations. And if you have a good enough simulator, you can take derivative in this context with respect to control parameters of the time-varying state and suppress these vibrations successfully. This also works on the physical robots. You see the before and after result, and we can actually suppress significantly the vibrations with an open-loop control technique. So we don't take sensory feedback into account. We've also worked with Marco Hutter and RSL on this project here. These are not fully actuated systems like the animatronics that we just saw, but they're under-actuated systems. So we wanted to see if we can take artistic input or motion capture data and transfer that over to robots of different proportions and mass distributions, as you can see here. Really fun project, a really fun collaboration. So ETH collaborations in general are very important to us here in Zurich. All right, so we talked about animatronics, basically the body of an animatronic. Animatronics are robots that act on stage, but we also work on soft robotics because animatronics have silicon skins usually. So let's talk about that topic for a moment. Still model-based tools. So in Zurich, we built a simulator and have improved this simulator over the years that can simulate the mechanical assembly with an attached silicon skin. So if you step the motors on your assembly, you can actually predict how the skin is going to deform. That's very important for artists to see if they can hit the artistic targets. But the simulators can also predict the mechanical performance, and only if both of them are good enough, you can actually build this robot and it will last. That simulator was used, for example, for this animatronic back in the day, the Navi figure, and I'm going to play this video for you.
I look forward to seeing you on Pandora. Well, not te cameya. Was that okay?
So this is a robot. It's not the character from the movie, but I think here Show Systems with our simulation tools has been able to bridge the gap between the physical and the digital world, so you don't see the difference as much any longer. This is how the robot looks like if you remove the silicon skin. Very complex linkages that are driven by electric actuators. And so our simulation tools have to scale to this complexity level. All right, so we also do fundamental research in the direction of soft robotics in general. I won't go into the detail here, but we looked into optimal actuation, optimal sensorization of soft robotic components. I'll point you to the review article if you're interested in this topic. All right, so the last robotic character that we want to talk about should be able to walk in uneven terrain, so learning-based tools are the best tools. And we have Ruben and Espen with me today. They worked on this project. This was designed in Zurich, this robot. That's how it looks like. It has 14 degrees of freedom, 5 in each leg, 4 in the neck. It has show functions, so show functions make them fun. We have antennas that move, we have a headlamp, we have eyes with displays behind them. We have speakers, so it can actually generate sound at the same time. It has a real-time PC and also a battery module, so it has the brains and power to actually freely walk around. So we wanted to give you a demo. So the robot can actually freely balance, so it can look at the audience, do any head motion, and the pelvis counterbalances. It can walk towards me, and while looking at the audience at the same time. So you hear it can generate sound at the same time. And so it can be happy. But if you're not so nice to the character, it can get really angry. And so you're in an interesting audience, so he can actually scan the audience. And because it's a fantastic audience today, he's very happy to see you all. Right? Thanks so much. So behind the scenes, we use reinforcement learning. We bring these robots into a simulation environment. We have perturbation forces to make sure that the control policies are robust. But that's not the secret sauce. That's basically pretty standard what we do here. The secret sauce is that we have artist-provided motion, and we want to follow that motion or imitate these motions while the robot learns to balance at the same time. So this is the secret sauce behind this. And if you train robust policies, you can have kids play with the robot, and it actually quite naturally reacts, for example, here, these stepping motions. We also trained it to walk blindly right now on uneven terrain. So This is useful because then you can bring it outside. Here, we brought it to a forest close to Zurich, close to our lab, and you can actually stably walk in those environments. Again, it's completely blind at the moment. So here you also have lots of perturbations due to the vegetation on the ground. All right, I hope I was able to convince you that model-based and learning-based tools, especially also the combination in the future of the two, allow you to build ever more expressive robotic characters, not just robots. This is the team here in Zurich, and we are actually growing. We have open positions, especially on the control side, so if you are interested in talking to us later, we are looking for talent at the moment. And thanks so much for all the internal and external collaborations, especially the ETH ones, which are incredibly important to us. Thanks so much.
Thanks very much, Moritz, for this wonderful presentation. Of course, this wonderful demo, I would love to have one at home. Hopefully, can get one soon. So there is time for questions. Who would like to start with a question? Over there.
Hello. It was a very fascinating presentation. Thank you. I had a question, more like a curiosity oriented. What's like the latest robot that you are working on, and what exactly it's going to do?
I mean, this is the latest one that we've basically just publicly announced a few weeks ago at IROS. So I can't, unfortunately, tell you more about the robots that we're currently working on. But what I can say is that we continue to just create tools to build robots like that, also freely walking and so on, and we want to push the boundaries of what's possible when it comes to building robotic characters that freely walk in the end. So I can't, unfortunately, answer that question better.
Other questions?
Thank you for the very nice presentation. You mentioned that, for example, this robot at the moment is completely blind, right? I was wondering, are you working also on solutions that can kind of interact with the humans that they encounter in the world, and do they have some perception to understand what those humans are currently doing or how they are feeling?
It's an excellent question. So absolutely. So this robot is already equipped with depth sensors, so perception is definitely something that is important to us. So it can actually also perceive its environment and walk even in more complex terrain. And the other question, guest interaction, absolutely. So we call it guest interaction because visitors to our theme parks are guests in the end. Interaction with guests in the future of people is very important to us, and definitely a research topic that is important in the future.
One last question over there in the...
Hello. Thanks so much for the presentation. I think I'd like to ask more about, so the focus was here reinforcement learning and imitating artist-shaped or artist-drawn movements, right? But the robot seems to have this sonic human-robot interaction, since that it imitates these sounds that convey intent, yep, and that we understand. And I'd say, what's the role of affect-aware interaction or affect awareness into your future vision for the robot? Do you deal with the affect-aware agents? Are you planning to make it, or to expand that research field, or is it more focused on learning-based control for now?
That's an excellent question. In the end, it's all puppeteered at the moment. So Ruben right now has a Steam Deck in his hand and is controlling the robot and also the sound. There is some sound that is generated. So based on the actuators and so on, we can generate sound while the robot is moving. But definitely we want to do more in that direction and do more autonomously in the future. It's an important topic. We can talk more later on.
So thanks very much again, Moritz.
Thanks for having me. Thank you.